So what we're going to do is calculate the relativistic corrections, with this term added on, to the energy of the harmonic oscillator, which we've solved all these little equations out here. So our equation has changed. Got to throw in this with naturally, with that extra small term, the solution will be different. The wave function will be slightly different, and the energies will be different. But this equation, as far as I'm concerned, as far as I know, does not have any exact solution. That's because of the form of the momentum operator. That'll be fourth derivative, whereas that's a second derivative. So you're actually having fourth and second derivatives, and the equation's not exactly solvable. Well, what do you do in such situations? You use perturbation theory. Now, what I'm going to demonstrate is only using non-degenerate perturbation theory, which means there's not, for a given energy, there's only one corresponding eigenvector to it. So I'm only going to use non-degenerate perturbation theory because for our example, our unperturbed system is non-degenerate as, the harmonic oscillator. So we're basically, I'm just going to run through first order perturbation theory. Okay, so we're going to have to do a format change here. I had multiple part videos of me explaining first order perturbation theory, non-degenerate, and unfortunately we accidentally did not save one of them, and today I do not have my camera person with me, and my board honestly is kind of hard to get to without rearranging my room. So I'm just going to make a quick video here for completeness sakes, kind of picking up where I had left off. So in terms of our Hamiltonian operator, we can label this right here as our unperturbed Hamiltonian, H hat 0, and this as our perturbed Hamiltonian operator. The idea of first order non-degenerate perturbation theory is that you basically describe an unknown solution as an approximation built around the one with the known solution, or the solvable system. In that case, our unperturbed equation, which is exactly solvable, and we know our unperturbed wave function, unperturbed energy. We can describe our new equation as unperturbed plus perturbation, unperturbed plus perturbation equals Now we're only going to consider first order products, like terms such as those will go to 0. These are small, and we're going to neglect these terms because they make these equations complicated, and we don't like them. We don't like complicated. Actually, we do. But so I'm going to perform this product, but I'm only going to keep the first order terms, and you can do this for second order or third order or however, and neglect however many terms you want to, but it gets more and more complicated to calculate. Like the jump from the first order to the second order in terms of complexity is very big. I've actually done the relativistic energy corrections for up to second order for the harmonic oscillator, and it took me a bit because you have to do a sum, and then there's a lot of terms involved. Anyway, so that's going to go to that. That's going to go to that. And we're going to neglect the extra terms, and we're going to equate that to the second hand side. That's going to go to that. Oh, I didn't even write it. What's delta E size 0? Times delta psi plus all the extra terms here. We're going to take those as approximately 0 and see what we got. Well, this right here, that's just our original equation, as seen right there. That's just going to go to 0. So we can cross that out. Or those cancel out. It's not going to go to 0 unless you subtract them. And that leaves us with us with, oops, it's not a plus, it's an equal sign. Alright, there we go. That leaves us with this equation right here. Okay, so we'll backtrack briefly. So before we move on to the next step, I want to explain something. Let's say you have a square integrable function, f, which means that the inner product of its with itself is finite. I mean, you can integrate it. It's square, or it's modulus squared, and get a finite number. And let's add two square integrable functions together and take their inner product with themselves. Or is this new square integrable function f plus g also square integrable? Well, we can write this out. Our condition is that this must be finite. Well, we already know, because they're definitions, the two individual ones are square integrable, so that's going to be finite. That's definitely. And from the Schwartz inequality, we know that that must obey this. That must be finite, or that's finite and that's finite by definition. So this is less than a finite number, essentially. Meaning that these individual components are also finite, meaning that if f and g are square integrable, then so is f plus g. With that knowledge in hand, we can write our perturbed, our full wave function Oh, and I should add that with the right coefficients, a plus b, g, you can normalize them. With the right coefficients, the right superposition of f and g, you can get it normalized to where the inner product is still equal to 1, which is desirable. So we can write this as just an arbitrary function. This must be square integrable. our perturbed wave function and our unperturbed wave functions must both be square integrable. As such, we can always write it as some superposition of square integrable functions. Well, we know a good set of square integrable functions. It's our original unperturbed wave functions, where they range from etc. corresponding to e sub 0, e1, e2. So we can write our unperturbed wave function, or our perturbed wave function total, as sum over m now. And we can write this, we can pull out the n term, which that psi 0 n is just our unperturbed wave function if you set c sub m equals to 1. Meaning that we can represent our unperturbed wave function like this, where you sum over all the states, the unperturbed states, minus the actual unperturbed state. And that's a helpful trick for what follows. So, to continue, we are going to move to Brocket notation. We're going to rewrite this equation here as we can write the perturbed wave function as so we can write this equation like this. Now let's take the inner product with psi 0n. Let's take the inner product over both sides. That's just our unperturbed expectation value, basically. Plus now note that when the oops, that was meant to be a h bar 0 acts on our unperturbed states. It's just going to give you e sub 0 m. That's just a number now. So when we take, that's really messy, you get a term like this. And because these are two basically m can't equal n. So these are two different states, and these are orthogonal to each other, and they have to be 0. So that whole term will vanish. And that's a constant, can be brought out to the opposite side. And similarly, that will also vanish. And you are left with our energy perturbation to first order approximation. So our unperturbed wave function with an inner product with our Hamiltonian perturbation mixed in, or sandwiched in between them. Basically an expectation value, in a sense. And you could, to get the perturbation of the wave function, you basically would have taken the inner product with some arbitrary state that was not equal to n, and you'd wind up getting a formula for CK, and you plug that CK back into the original formula, and blah blah blah, and you'd get our perturbation. But we're not going to use that in the following calculation. So anyway, back to standard format.